Welcome back everyone to MAE170. This is lecture 4 in week number 2. Just a quick recap of what we've seen so far. We saw how to solve linear time invariant ordinary differential equations using the Laplace transform methodology. We take the ordinary differential equations, which are equations in the time domain, and by applying the direct Laplace transform, we switch from the time domain to the complex frequency domain S, and we can therefore solve the equation that now is going to be an algebraic equation. We found that the solution is going to be expressed as a fraction with the numerator and a denominator. In order to go back to the time domain, we need to simplify this fraction by applying the partial fraction expansion. So what we're doing, we are rewriting the output as a sum of a bunch of small fractions, and then we can take the inverse Laplace transform of all these minor fractions. By doing so, we can go back from the S domain to the time domain and have the solution to the original ordinary differential equations in the time domain. The other concept that we saw is the transfer function. And in short, the transfer function is the ratio between the output and the input when the initial conditions are set to 0. Finally, we saw how to work with block diagrams. In particular, we saw how to reduce block diagrams. What we're going to do, we're going to find n+1 equations. N is the number of all the sum injunctions that you can find in the block diagram, and 1 is or refers to the output. All right, so today we'll start talking about the final or steady state value. So the two things, there are two ways to call the same thing. Sometimes I can refer to as the final value or the steady state value. These are both terms that are widely used in control systems. So get familiar with both. Why is it important? Well, sometimes more than the evolution with respect to time of the output, we might just be interested in its final value. So it's important that we know how to compute the final value of a function. Now, forget about the proper output of a control system. Just think about a generic function in the time domain. So the final value is the value for the time that tends to infinity. And this is known as the final value. So for a generic function in the time domain, the final value or steady state value is defined as the limit for time that goes to infinity of y of t. As simple as that. Let's take a look at a few examples of some functions. If we have an exponentially decaying function, well, its final value is 0. So in this case, we have that the steady state value for y of t is equal to 0. As time increases, the function decreases and asymptotically converges to 0. We can also have another example of a function that approaches asymptotically a finite value. And let's say that this value is a. So in this case, the steady state value is equal to a. There can be other functions, of course. What if we had a harmonic function? Well, in the case of a harmonic function, we have that the function oscillates between a maximum and a minimum value. So there's not really, if you remember, when you take the limit for time that goes to infinity of a harmonic function, that is sine of t or cosine of t, well, that is not defined. So if we have purely harmonic functions, the steady state value is not defined, simply because the function will keep oscillating between a maximum and a minimum value, and it will never approach a finite value. Another example of functions that do not possess a steady state value is a function that diverges. For instance, we can take an exponentially growing function. If you take the limit as time goes to infinity of such functions, well, you will find that that is infinity. So in case 3 and 4, the steady state value of a function is not defined. So the final value or steady state value is defined if and only if such value or the limit for time that goes to infinity of y of t is finite. Finite includes 0, okay? It has to be equal to a constant value. All right, well, here we have the steady state value defined in the time domain. However, there's a very convenient theorem called the final value theorem that allows us to compute the steady state value of a function even when we are in the S domain. So we don't really have to go back to the time domain to find the steady state value, and that is really convenient. So let me just give you the statement for the theorem in form of a formula. So we have that the steady state value of a function y of t, well, in the time domain, as we said, is the limit for time that goes to infinity of y of t. But that is also equal to, in the S domain, to the limit for s that goes to 0 of s times y of s, where, of course, y of s is the Laplace transform of y of t. Now, I'm going to put an asterisk here because this is not always valid. We have to check a couple of conditions. And let me show you a couple of examples that show you when we can and when we cannot apply such theorem. This is very important to remember. Let's take the example that we saw in lecture 3. So we actually, in lecture 3, we started from the output in the S domain. Here, what I'm doing, I'm giving you the ODE in the time domain with an initial condition and with an input, then find the Laplace transform, therefore an algebraic equation. I solve it, finding the output. And now we can go back to the time domain, apply the Laplace inverse transform. We've done that, or we did it in lecture 3. And so we have that in the time domain, y of t is equal to 1/2 minus 1/2 times e to the power of minus 2t. All right, let's calculate the steady state value or the final value using the definition in the time domain first. So we have that the limit for time that goes to infinity of y of t, that is the limit of 1/2 minus 1/2 times e to the power of minus 2t. All right, so if t goes to infinity, this term will just go to 0, and so we're left with simply 1/2. Let's now apply the final value theorem, and let's try to compute the same value in the S domain. That is, we'll take the limit for s that goes to 0 of s times the function in the s domain. So we have the limit for s that goes to 0 of s times, so we need to look at this, 1 over s times s plus 2. We see that s cancels out, so we're left with 1 over s plus 2. If s goes to 0, we're left with 1/2. So you see here that we're getting the same value. And in this case, the final value theorem actually gives us the right answer. Let's now take a look at an example in which this doesn't really happen. So let's consider this function in the s domain, 1 over s times s minus 2. So if we want to find the steady state value, just applying the final value theorem, we would do s times y of s. And so we have that s cancels out, s tends to 0, and so apparently we are left with minus 1/2. Now, is this correct? Well, let's verify it in the time domain. So this is also a good exercise to apply the Laplace inverse transform. So y of s, we can write it with the partial fraction expansion as a over s plus b over s minus 2. The two roots are 0 and plus 2. They're different, so we can proceed in the normal way. So now we have to find a and b. So we have as minus 2a plus b times s. And so this gives us, in short, a equals 1 minus 1/2 and b equals to plus 1/2. So y of s is minus 1 over 2s plus 1 over 2 times s minus 2. Applying the inverse Laplace transform, minus 1 over 2s is simply minus 1/2. Sounds promising. And now the Laplace inverse transform of the second term gives us plus 1/2 e to the plus 2t. So if we want to take the steady state value in the time domain, take the limit for time that goes to infinity of y of t. And you see that the second term grows exponentially and goes all the way to infinity. So the limit of y of t as time goes to infinity is actually plus infinity. So these two results are not the same. So what happened? Well, that is because, as I suggested, the final value theorem applies if and only if there are two conditions that are met. So these two conditions are the following. If we have a function in the S domain, and we're considering in the S domain because that's the whole point of the final value theorem. We want to find the steady state value without having to transform back into the time domain. So if we are in the S domain and we have a function that is our usual fraction with the numerator and a denominator, so n of s over d of s, then these two conditions have to be met. So we have to compute the roots of d of s equals 0. And then we have to verify that the non-zero roots of d of s, so all the roots that are different than 0, must have negative real parts. Condition number 2 says that if instead the roots of d of s are exactly equal to 0, so that means that both real parts and imaginary parts are equal to 0, we would just say, well, that's just equal to 0. Well, we can have at most one of them. So the multiplicity can be at most 1. So let me repeat. Once we compute all the roots of this equation, d of s equals 0, well, we write them down and we see how many 0 roots do we have. If we have more than 1 0 root, that condition number 2 does not apply. And for all the non-zero roots, we take a look at the real part of them. If they all have negative real parts, then the final value theorem applies. If just one of these roots have positive real part, well then, or even 0 real part, then it does not, the final value theorem does not apply. Now, this is very important because we're going to use this terminology very often. Given a function with a numerator and a denominator, then the roots of n of s equals 0 are called the zeros of the function y. And we usually write them as z1, z2, all the way to m, where m is the degree of the polynomial n of s. We can do the same thing when we solve d of s equals 0. Now, the roots of these equations are called poles of y of s. How many poles do we have? Well, we have 1 all the way to n, where n is the degree of the polynomial d of s. Conveniently, we can also visualize the two conditions for the application for the validity of the final value theorem using the S plane. Since S is a complex frequency, that is a complex number, it has a real part and an imaginary part, then we need to use a plane to visualize complex numbers. And since the two conditions for the applicability of the final value theorem focus on the roots of d of s equals 0, or in other words, the poles of y of s, we are only interested in the location of the poles. And the two conditions, if you want to summarize them graphically, we are allowed to have poles only in the left plane. This is okay. Whereas in the right of plane, including the imaginary axis, this is not okay. However, we have that the origin, that is when the root is equal to 0, is also okay if we have at most one pole at the origin. There's also another useful thing when you're representing zeros and poles of a function in the S-plane. Everything has to be symmetrical about the real axis, and that is because of the fundamental theorem of algebra that we saw last time. In fact, when we have complex roots, they must be complex conjugate. That is, the real part is the same. Let's say that we have a point here, then we also must have its complex conjugate down here. Another thing that you'll get very familiar with is how to represent poles and zeros of a function in the S-plane. So for the poles, we use an X mark. And for the zeros, we use a circle. All right, so now let's take a look at another couple of examples with two functions in the S domain. We'll find the zeros and the poles, and by inspecting the poles, we'll see whether or not the final value theorem can be applied. All right, so we're given the following function in the S domain. We have S plus 1 over S times S plus 4 times S plus 2 minus I times S plus 2 plus I. The function is already factorized, so it's easy to find the zeros and the poles. Let's take a look at the numerator, and we see that we have just a polynomial 1 degree. So if we equate that to 0, it's easy to find that the roots of such equation are just equal to 1. So we have only 1 0, and that is equal to minus 1. So we have 1 0 equals to minus 1. What about the poles? Well, we need to take the denominator and equate it to 0. In this case, we have 4 poles. So we have P1 equals 0, P2 equals to minus 4, and then P3 and 4 are equal to minus 2 plus or minus I. This makes sense. We have P1 and P2 are real numbers, and P3 and P4 are complex conjugate. So everything checks out in terms of the fundamental theorem of algebra. Now, why did we find the poles? It's because we want to see whether or not the final value theorem applies. So we need to check the poles and check the two conditions. First of all, let's check condition number 1. We need to find the non-zero poles, in this case, P2 and P3 and 4, and we need to check their real parts. So the real part of P2 is minus 4, that's negative, and the real parts of P3 and P4 are minus 2, which are also negative. So condition 1 is met. What about condition 2? Now we have to check the zero poles. We only have 1 0 pole, so we're fine. In other words, the multiplicity is equal to 1, which satisfies condition 2. We can therefore conclude that the final value theorem can be applied. And so we can find the steady state value by taking the limit in the S domain, which is much easier. So in this case, S cancels out, substituting S equals 0, we're left with 1 over, and here we have 4, and here we have 4 plus 1, 5. So 4 times 5 equals 20. So the final value of this function is equal to 1 over 20. And if you want, and I strongly suggest that you do so, check using MATLAB plotting y of t. So what you need to do is take the Laplace inverse transform, find y of t. It's a good exercise. It can be asked in the midterm, for instance. And take the limit for t that goes to infinity. One thing before moving to example number 3, what we can do is we can place the 0 and the 4 poles in the S-plane. And so we can also graphically check the validity of the final value theorem. So I'm going to use the same color, green color. So starting with the 0, we had a 0 at -1. Zeros do not have anything to do with the final value theorem. So it doesn't really matter if we have positive or negative zeros. We only care about the poles. All right, so the 4 poles are: one was at 0 or at the origin of the S-plane. Then we had another one at -4. And the other 2 were at -2 plus or minus I. So here and here. In MATLAB, there's a very convenient way of finding the poles or plotting the poles and the zeros, and that is by using the function pzmap or pzplot. They're pretty much equivalent. All right, let's take a look at a 4th example. And we're actually considering the same example that we saw earlier. So this should really be equal to example number 2. All right, so we have that y of s is equal to 1 over s times s minus 2. Let's go step by step. How many zeros do we have? Well, we have to check the numerator. The numerator is simply 1. The degree of the polynomial is 0, so we don't have any zeros. What about the poles? We have 2 of them. We have 1 at 0 and 1 at 2. So starting with the pole at 0, well, we have its multiplicity is equal to 1, so condition 2 is checked. But when it comes to the non-zero poles, in this case, the non-zero pole, the real part is positive, is equal to 2. So condition 1 is not met. Therefore, the final value theorem cannot be applied. So we verified that earlier on by directly finding the final value applying the limit in the time domain. But if we didn't want to retransform the function in the time domain, what we can do is just check, can we apply the final value theorem? Yes or no? Well, here it shows that we cannot do so. And so if we wanted to find the final value, we would have to apply the limit in the time domain. Lastly, we can also plot the zeros and the poles of the second function in the S-plane. And in this case, we don't have any zeros. We only have 2 poles, one at the origin, so this overlaps, and the other one is at +2. Okay. We've talked about the final value theorem, but there's also the initial value theorem. This is not very used because normally we know where we start from, but we don't know where we end. But just in case we want to retrieve our initial state, then we can apply the initial value theorem. And this is given by, it's very similar, but now the limit is taken for time that goes to 0, plus it means that we're approaching it from positive numbers of y of t, positive numbers in terms of t, of course. That is equal to the limit. And now s, guess what? Now the s goes to infinity. So it's always, can think about it as the one is the inverse of the other. So if t is 0, then s is infinity. If t is infinity, then s is 0. Because s is a frequency. So the higher the time, that is the period, the lower the frequency. And if the period tends to infinity, then the frequency tends to 0. And if the period tends to 0, then the frequency tends to infinity. You can think about it in these terms. And so what are we taking the limit of? Same thing, s times y of s. Now, what are the conditions for which the initial value theorem applies? Well, this is much easier to see. This applies if and only if y of s is strictly proper. That is, the number of zeros of y of s is less than the number of poles. For instance, if we had a function equal to s plus 2 over s squared plus 3s plus 4, well, we only have 1 0 and 2 poles because the degree of the polynomial at the numerator is equal to 1. So we're going to have only 1 0, in this case at -2. And then we have 2 poles because the degree of the polynomial at the denominator is equal to 2. So I'm going to stop this video here. And in the second part, we're going to talk about errors for the feedback control systems and the concept of system types. So again, I'll divide the lecture into 2 videos. So you can decide to watch one or rewatch, I should say. You should watch both of the videos, but then to rewatch one part or the other. All right, I'll see you in part 2.